Hi everyone, today we're going to talk about topic 9.10, cell potential under non-standard conditions. So far we've described electrochemical cells that are at standard condition. In other words, it's at 1 atmosphere and 1 molar concentration. But oftentimes we don't have cells that are at these standard conditions. We have cells that are at non-standard conditions. When we have a cell that's at non-standard conditions, we used what's known as the Nernst equation. The Nernst equation says that E, which is the non-standard cell potential, is equal to E naught of the cell, which is the standard potential, minus RT over NF times the natural log of Q, where, of course, Q is the reaction quotient. So if you're at non-standard conditions, you could find this by using just the regular cell potentials and then plug it into this equation. So let's take our example of the zinc and copper cell. So we have Zn2 plus 2 electrons. We'll make Zn, and this has a reduction potential of negative 0.76 volts. The copper reduction potential looks exactly the same. This has an E naught of negative 2.87 volts. Of course, this is a larger number, and so this is the cathode, and this is the anode. And so for the whole cell, this value would be negative 0.76 minus negative 2.87 volts, which gives us 2.11 volts, which is a positive number. And again, as a reminder, this is under standard conditions. So if I have a 1 molar concentration, I would stop right there. But let's assume that we are not at standard conditions. In other words, let's say that the concentration of Cu2 plus is 2 molar and the concentration of Zn2 plus is 1 molar, right? So I've doubled the concentration of just one of them. We would use the Nernst equation. So E is equal to E naught, which we calculated here is 2.11 volts. This would be minus R, and for R we use 8.314 joules per mole times Kelvin. T, which is 298 Kelvin, just for the sake of this example, let's say we're at room temperature, divided by the number of electrons, which is 2, because I have 2 electrons up there in those equations. And this will be times 96,485 coulombs per mole. And then we'd multiply all of this by the natural log of Q. And so now we have to look at this equation to figure out what my expression for Q is, because I obviously have 2 different equations here. We want just one. So I'm going to bring this down here. And remember, if I have these 2 half reactions, I can combine them together to make a full reaction. For the larger one, we can keep that one the same because that's what the actual reduction is. So Zn2 plus 2 electrons makes Zn. Zinc is actually the one being reduced, so I keep that the same. And for copper, I just flip it. Cu makes Cu2 plus 2 electrons. And I can just add these together. So my reaction is zinc 2 plus, aqueous, plus solid copper, reacts to make copper 2 plus, and solid zinc. Now with this equation, I can have an expression for Q, which remember is just the equilibrium constant, but just not at equilibrium. And so all it is products over reactants. Therefore, it's the concentration of Cu2 plus divided by the concentration of Zn2 plus. And so now, all we got to do for this is plug in our values that I have up here. For copper 2 plus, this is 2 molar. And for Zn2 plus, this is 1 molar. And so in order to calculate the cell potential under non-standard conditions, where I have 2 times the concentration of copper 2 plus, this is the equation that I would use to calculate that. Now, I'll save you all the details of the math, but if you do all of this, we essentially get 2.10 volts. So in the situation where I have twice the amount of copper, my cell potential goes down slightly. Now notice my E is less than E naught, right? It went down by 0.01, a really small amount, but it still went down. If we think about this in the context of Le Chatelier's principle, what I did is I added products, right? Because my copper 2 plus was higher, and my copper 2 plus is in the products, as we see right here. Because it did that, it means the forward reaction becomes less favored. Because remember, in any electrochemical cell, it's a spontaneous reaction, and so the forward reaction must be favored. If I add products, that makes the forward reaction less favored, and so I prefer reactants slightly, very slightly, more than before. So E goes down. And as a rule of thumb, and we should be able to predict this given the conditions, if your products are higher concentration, then E is going to be less than the standard reduction potential. If your reactants are higher concentration, then it's the opposite. E is going to be slightly bigger than E naught because your reaction is going to prefer the forward direction even more because I have so much more reactants. And so at the end of the day, we end up with these three different relationships that we can use to look at equilibrium, free energy, and cell potentials. The relationship between delta G and our cell potential E naught is delta G equals minus NFE. Then you also have a relationship between delta G and K, which is delta G equals negative RT log K. And again, remember these are all at standard conditions. Which, as a reminder, 1 atmosphere, 1 molar, 298 Kelvin. And then now we also have this relationship, which is part of the Nernst equation, which says that E naught is equal to RT over NF times the natural log of K. And so we can use all of these three different relationships to jump back and forth between these different parameters that all fit our electrochemical cell. Now, a consequence of the Nernst equation is that we have something called a concentration cell, which is an electrochemical cell with the same compound or element at the anode and cathode, but the only difference is they have different concentrations. Right, and so a concentration cell is essentially just an electrochemical cell that has the same thing at the anode and cathode, but they're at different concentrations. For this, the standard reduction potential is equal to 0, but Q is not. And so E, right, the non-standard reduction potential, will not equal 0. And so we can use the Nernst equation to calculate a concentration cell, which I'll show on the next slide. And so what we see here is that we have a nickel anode and a nickel cathode. You have a salt bridge, just like any other electrochemical cell, and it goes from anode to cathode with a very small reduction potential, 0.09 is the cell potential. In our anode, the concentration of nickel 2 plus is 1 times 10 to the negative third, but in the cathode, it's 1 molar. Because of this difference in concentration, we still have a current. It will still flow from anode to cathode, but if I have the same concentration, this is the standard condition, or it's slightly non-standard because it's 0.5 instead of 1 molar, but in this case, we're not going to get anything because we have the same concentration at the anode and the cathode. And so what this basically says is that at different concentrations, you can still make a cell. This is what we call a concentration cell. Now, what this discharge thing here is saying is essentially that over time, we'll have that electron flow, but of course we're going to reach a point where the concentrations are equal because, right, we have electrons moving from one end to the other. And so at our anode, we're going to have our oxidation reaction happening, and that will continue to happen. At our cathode, you'll have the reduction happening over and over and over again, and eventually you'll reach a point where the concentrations now become equal and you have the same amount of nickel 2+ on each side. Now let's look at this example right here. What we're given is this electrochemical cell. We have Mg right here at the anode, and we have Ag, or silver, at the cathode. And we can see that we have a standard reduction potential of 3.17 volts. And so it says it generates a cell potential of plus 3.17 when operated under standard conditions. It says they make a second cell made from the same two metals, and the measured cell potential is at 3.25. So what happens is the second cell, E, is greater than E0, right? And the second cell that's under different conditions, it is a higher potential than when it is at standard conditions. It's saying which of the following could be the reason for the second cell having a greater cell potential. Now, if you remember from a few slides ago, I said that if E is greater than E0, this means that the reactants are higher concentration, which means the reaction wants to go forward more than it wants to go backwards. First thing we got to do here is to think about the overall reaction, because then we can know what's in our reactants and products. Now, this number here, this reduction potential for silver, is higher, and so this will be the reduced end. And for Mg, it's lower, and so this will be oxidized. Remember, oxidation is loss, reduction is gain, and so we need to flip the oxidation reaction. So here we get Ag plus, aqueous, plus 1 electron, makes solid Ag. And then we have to flip the magnesium reaction. So we have Mg solid is going to break apart to make Mg2 plus 2 electrons. Now, of course, my number of electrons here isn't equal. So what I need to do is multiply this top reaction and then add them together. We'll see that the electrons will cancel out. So I get 2 Ag plus 1 solid magnesium. That's going to make 2 solid Ag and Mg2 plus. And of course, the electrons will cancel out. And so now this is my reaction. And again, just like I had said, what we need to think about is our reaction quotient Q. All we do is products over reactants. Remember, we can't include any of the solids. So this is concentration of Mg2 plus over concentration of Ag2 plus squared, right? Because that 2 ends up being squared in the reaction quotient. And so now we can look back at our observation, right? This says here, well, we can actually look at the answer choices first and see if some of them make sense more than the other one. Answer choice A and B says the mass of the Ag electrode is, or the Mg electrode is higher than in the first. And if we look back to the notes, we can easily see that mass of the electrodes, or mass of this piece of metal, it is unimportant. We don't really care about the mass, we care about the concentration. And so A and B can't be our answer, because we don't really care about the mass of those electrodes, we care about the concentration in solution. And so answer choice C says that the concentration of Mg2 plus is higher than 1 molar, and Ag is 1 molar in the second cell, which makes Q greater than 1 for the second cell and Q equals 1 for the first. Answer choice D is the exact opposite. This says that the Ag is higher, which makes Q less than 1 in the second cell and Q equals 1 in the first cell. Well, we know in the first cell that we're at standard conditions, and so Q must equal 1 in both of them. And so now all we got to do is look at our situation right here. If we remember the Nernst equation, it's E equals E naught minus RT over NF natural log of Q. And so because we're subtracting, if this entire term goes up, then E should go down. If the entire term goes down, then E should go up. We can see here that E is greater than our standard, E0. And so this entire term must have gone down. The only case in which this entire term goes down is if Q is less than 1, which is exactly what we see here, right? Our Ag concentration must be higher, and so the only answer choice that makes sense here is D. If our potential had gone down, as in the second cell it was lower than the first one, then C would be our answer. Because our potential goes up, that means that Q must be less than 1, and if Q is less than 1, that means that E must be greater in the second cell than in the first. We'll discuss this more in class and go over some more problems, and I'll answer any questions y'all have, but for now, that's all. Thanks, guys.